already started. I hope that everyone is okay with that. And the presentation will be recorded and also be available later after Christmas. Then the next webinar should be held in February with the same format. This format is a first trial. We took the lead, FP Innovation, for this first webinar. Hopefully, the next webinar will be on the same format, and the topic should be fire performance of Towerwood and mid-rise building. Then let's start with the first presenter. Will be Pierre Landel from Rise. Yeah.
Okay. Can you see anything?
Yes.
And you can hear me then. Yeah. Yeah. Good.
Yes.
Okay.
Good.
All right. So good morning, America, and good evening, Europe. So thanks for the nice introduction, Silva. I'm honored to be here, the first speaker for this first webinar. Yeah, my name is Pierre Landel. I'm a researcher at RISE, the Research Institute of Sweden. And I'm also a PhD student at Linnaeus University. And today my talk will be about top acceleration. I will show some effects on the serviceability using different building codes and different wood building systems. Here on the right, as you can see from the picture, so we are now in the north of Sweden, erecting a tall timber building with full CLT structure. It's called Sara Culture House, and the hotel will be in the top of the, or in the tower here. So first I will talk about why and how to design for good serviceability. Then I will present some different building codes and I will compare them. And finally, I will show some results from a Swedish project where we studied conceptually how to design 22-story timber buildings. And that could have resulted in one of the side result is this one. It's also the Sara Culture House that actually this week reached its full height. And on the picture you can see the two stabilizing shafts made of 80 centimeter thick CLT walls, mainly due to serviceability for wind-induced vibration. So it can be, it's important to look at that when you want to build higher. Any question or any unmute? Maybe. Okay. Okay, let's start. The phenomena of wind-induced vibration is quite easy to understand, but maybe a bit harder to predict. The wind is blowing on tall, light, flexible structures, and that induces dynamic response of the structure or lateral vibration or motions. So this is a structural and fluid dynamic phenomena. And in the case of tall buildings, the response might then has an impact on the serviceability. Sometimes we also talk about habitability or comfort.
Je comprends pas pourquoi j'ai pas de son là, c'est chiant.
Yeah, for me too, I had some trouble with the counter. Can you write Sylvain in the chat because they can't hear us? Or if you can mute.
Ouais, je sais pas c'est qui parle, c'est pour ça.
Yeah, because it was, maybe it's not easy the first time to get the sound. It was the same for me before. But let's continue. So this is a problem, a structural dynamic phenomena, and there are mainly three parameters that govern the response of a structure to a given excitation, here the wind, and the three are the mass, the stiffness, and the damping of the structure. So then depending on the characteristic of the wind-induced motion at the top, people inside the building might feel the motions, and even get seasick or scared that the building might collapse. And at a lower level of motion, even below perception, but often for longer duration, some studies have shown that people can express SOPIT syndromes with symptoms like insomnia, dizziness, depression, or reduced ability to perform tasks. So today the best and simplest way to design tall buildings for good comfort at the top is to keep the horizontal accelerations below some recommended acceleration limits. So let's see some of the recommendations that we can find. First type of guideline focuses on the peak acceleration here on this vertical axis, which is from the ISO 10137 from 2007. And the limits for serviceability are dependent, as you see on the graph, they are dependent on the frequency of the motion on this horizontal axis. So we can notice that below 1 Hertz, we become less sensitive as human people. We are less sensitive to vibration when the frequency decreases. Here, F0 is usually the first natural frequency of the building in the direction of the motion. At the meantime, the wind gust energy is often higher at frequency below around 1 Hertz. To be helpful for serviceability design, the guideline is considering relatively recurring events of motion, namely 1 year return period. It's also fine also to use this ISO standard for maybe 2 year return period. And the curve 1 here, this one is suitable for building with daily occupation, like offices, and curve 2 below is more suitable for residential building where people sleep or rest. And this curve number 2 is defined in the ISO standard to be close to a 90% level of the perception probability of motion. This ISO standard is mentioned in several countries, in several codes from several countries, but also those countries might recommend also some other limits that are just linearly and not dependent on frequency. And for residential buildings, they are usually around 0.1 or 0.2 meter per second square. But it might be that you look then at 5 year or 10 year return period. Another type of guideline, a bit older, use the root mean square acceleration. It's a kind of mean value of the variation here upon a 10-minute storm. And so this is the ISO 6897 from 1984, which is also frequency dependent. And the relationship with the peak acceleration is given here. It's a factor, the peak gust factor, which is usually around 3.5 or 4. And here this curve 1 is suitable for residential but also commercial office. It's the same curve. It's based on the 5-year recurrence of a storm. And what is interesting in the definition of this curve, it's the probability that 2%